Hello future engineers, subscribers, viewers, and students. Here is a video in Differential Calculus 4 and we're going to consider the following topics. Time rates 2, second part, parametric equations, slopes in polar curves, radius and center of curvature, and partial differentiation. So I divided this part into two, and in this part I'll present just two examples, and for the second part we'll have series of examples. So let's consider first parametric equations. When we encounter both x and y as functions of a third parameter t or omega or theta, then we have y prime still dy dx, and we define dy dx or y prime this time as the derivative of y with respect to t divided by the derivative of x with respect to t. So that will still be dy dx. So second derivative therefore is the derivative of dy dx. So it's the same. So note that the derivative of y with respect to x is a function of t and not x this time. Then let's develop formulas for slopes in polar curves. So take note that if we have a polar curve, then the tangent to it is the tangent line. The slope of the tangent line to it is the tangent of the angle that the tangent makes with the horizontal. So this is from the pole to any point on the curve, that's r, and that r makes an angle theta with a positive x-axis. The measurement is counterclockwise positive. And we have a tangent which makes an angle of alpha with the positive x-axis. Then the slope is the tangent of that angle alpha, which is dy dx. So in polar form, we have the relationship x r cosine theta and y r sine theta. So in this figure, we have to superimpose the Cartesian coordinates, is the polar axis, which coincides with the positive x-axis, and that's still the y-axis. So in terms of r and theta, this x here is r cosine theta, then the y is r sine of theta as shown. So beginning with y equals r sine theta, we're going to define dy d theta. And dy d theta, we have derivative of product r cosine theta, then plus sine theta times derivative of r dr d theta. Likewise, x is r cosine theta, so r dx dt or dx d theta is equal to r times negative sine theta plus second cosine theta times dr d theta. We then set up dy dx, which is the slope of the tangent to the curve. M is tangent of alpha, and it is derivative of y with respect to theta over derivative of x with respect to theta. So substituting these values, dy d theta is r cosine theta plus, let's denote r prime, so times dr d theta all over dr d theta times cosine theta minus r sine theta. Rearranging, and we note that dr d theta may be replaced by r prime, so slope is r cosine theta plus r prime sine theta over r prime cosine theta minus r sine theta. So that's the expression for slope, and we defined r prime here as derivative of r with respect to theta. So we consider next center of curvature, radius of curvature first. So we have to consider an arc. Then 2 points that are very close. So curvature is defined as the rate of change of direction per unit arc. So that is K is differential alpha over differential S. And to illustrate what radius of curvature is, or curvature is, so we have here the tangent to the curve, and the tangent makes an angle of alpha with the positive x-axis. That's the point of tangency. Then another point of tangency, so we have a slight change in the direction, and the angle between them is differential alpha, and the length or the distance between these 2 points considered, it's very close. I'm just exaggerating it here so that you can see, and so that I can explain it well. So the angle that the tangent makes with the positive x-axis is alpha, and the change in direction differential alpha, and this length here is differential s. So they meet at the center of curvature, which forms an angle. So these two are radius or radii form an angle which is also differential alpha. Angle between radii is also the angle between the tangents. So this is ds, and that is differential alpha. So because the reciprocal of curvature is the radius of curvature, then from arc length equals radius times central angle. So S equals radius times central angle, that's the radius. So that means differential S is R times differential alpha. So we then set up that differential alpha divided by differential S is 1 over R. And so we replace differential alpha over differential S here by K, and it is differential alpha over differential S, which is R times differential alpha. So we can cancel differential alpha and show that indeed curvature is the reciprocal of curvature. So curvature is absolute value of differential alpha over differential S, and radius of curvature therefore is, because the radius of curvature is the reciprocal of curvature also. So that is absolute value of differential S over differential alpha, because radius is supposedly positive, always positive. It should be that way. So from slope equals dy dx, and it is tangent of alpha here. So that's it. We have ds, which is radius times differential alpha. So slope is dy dx, and it is tangent of alpha, tangent that the tangent makes with the positive x-axis. And alpha therefore is inverse tangent of dy dx, or arctan of y prime. Then remember the original variable is x. So this is alpha equals arctan of u. It's like arctan of u, and differential of alpha is differential of u, or differential of y prime times differential of x divided by 1 plus u square. So differential alpha therefore is y double prime times differential of x all over 1 plus y prime square. So from differential s, which is by Pythagoras square root of dx square plus dy square, if we multiply and divide this expression by dx, and the denominator dx inserted into the radical, then it becomes dx over dx square, or dx square over dx square, which is 1, plus dy square over dx square, or dy dx quantity square. So that's the expression for dx. Therefore, curvature, which is differential alpha, y double prime dx over 1 plus y prime square divided by differential s square root of 1 plus y prime square dx. So we cancel out dx and we can combine 1 plus y prime square and square root of 1 plus y prime square. So curvature therefore is y double prime over quantity 1 plus y prime square raised to 3 halves. So if that's the formula for curvature, the radius of curvature, which is positive, is equal to quantity 1 plus y prime square raised to 3 halves all over absolute value of y double prime. So it's just the reciprocal of curvature also. Then finally, we have to consider center of curvature. And from the figure, if we denote this with h comma k, and because this point is at maybe point of tangency x1 comma y1, and if that is alpha, the angle between the vertical angle of inclination alpha, the angle between the vertical and the normal, which is r here, is also alpha. So that means h is x1, then minus, because it's going to the left, minus r times sine of this angle, so sine of alpha. So if that's the curve, we have point of tangency, angle that the tangent makes with the positive x-axis is alpha, and that's the center of curvature, angle that this radius, which is perpendicular to the tangent, makes with the vertical is also alpha. So that's r. That's the center, h comma k. Let's just call that. This is alpha. Then we can form this right triangle. So if we denote this as x1 comma y1, then this is r sine of alpha, while the vertical distance is r cosine of alpha. So that's r sine alpha, r cosine alpha. So x1 equals, h is equal to x1, then minus r sine alpha. Replacing sine alpha from, so let's form a right triangle first. Then let's define tangent of alpha equals y prime, so y prime over 1. So if that's alpha, this is y prime, this should be 1, and the hypotenuse should be square root of 1 plus y prime square. So that means sine of alpha is y prime over square root of 1 plus y prime square, and r is given by that expression. So h equals x1, quantity minus r, which is this. Then sine alpha from this right triangle is opposite y prime over square root of 1 plus y prime square. So we can cancel 1 plus square root of 1 plus y prime square, leaving here 1 plus y prime to the 1. And therefore h is x1 minus y prime times 1 plus y prime over y double prime. So x1 minus y prime times 1 plus y prime square over y double prime. K is equal to y1, then we go up plus r cosine of alpha, and replacing r by 1 plus y prime square to the 3 halves over y double prime, and cosine alpha is 1 over square root of 1 plus y prime square, and we can cancel that. Therefore k is y1 y1 plus 1 plus y prime square over y double prime. So we don't need to memorize it, but you just remember the formula for r, and in this triangle, then you can derive h x1 minus y prime 1 plus y prime square over y double prime, and k, which is y1 plus quantity 1 plus y prime square over y double prime. So that's for k. That's k. Then lastly, let's have partial derivatives whenever a function is function of variables like x, y, z, and so on. Then partial derivative of z with respect to x is differentiating the function with respect to x only, and we only treat x as the only variable. All other variables or symbols that appear are considered constant. So that's it for this portion. So in this part, we'll just consider two problems on time rates 2. This is the first. As a bicyclist moving at 6 meters per second passes a point, a balloon 8 meters directly above him rises at the rate of 2 meters per second. So how fast is the distance between the balloon and the bicyclist changing after 3 seconds? So here is the situation. We have the bicyclist here moving at 6 meters per second, and as it reaches this point, a balloon overhead 8 meters above him is rising at the rate of 2 meters per second, so that after a time t, the distance moved by the balloon or rose by the balloon would be 2 speed times time, so 2t. Likewise, the bicyclist will also be in this position, and this distance from this moment, from this um, situation or instant, is 6 times time, speed times time. So we have here the distance between the balloon and the bicyclist at any time t, and we form here a right triangle. So S is square root by Pythagoras theorem, square root of quantity 6t square plus quantity 8 plus 2t square. And this expression is enough to differentiate S with respect to time, the required here. Then the time is 3 seconds. So using your calculator, high-tech calculator, then this can be evaluated with t equals 3 seconds. And the answer is ds dt is 5.964 meters per second. So likewise, I also present the traditional solution, which is first we combine like terms. So 6t quantity square is 36t square, and we have 2t quantity square here, so that makes it 40t square, square root of 40t square, then plus 64, then plus the product of this is 32t. So S is square root of 40t square plus 32t plus 64. Differentiating with respect to time, so this, imagine this is u, so the derivative of square root of u is derivative of u with respect to t, the variable here, so which is 80t plus 32 divided by 2 square root of u. So we just copy that. So 80t ds dt is 80t plus 32 over 2 square root of u. So 2, we copy these three terms. Then we evaluate this ds dt expression with t equal to 3 seconds, and the answer is the same, 5.964 meters per second. So for the second problem, and last for this video, an airplane flying at a constant speed of 360 miles per hour and climbing at an angle of 45 degrees passes over a point P on the ground at an altitude of 10,560 feet. Find the rate at which its distance from P is changing 1 minute later. So let's have the figure. We have a horizontal ground and a point P, then the airplane is overhead. Distance 10,560 feet. Notice that 10,560 feet is 2 miles because 10,560 feet divided by 5,280 is 2. And at that instant, the plane is inclined 45 degrees and moving at 360 miles per hour. So this is the situation. This is point P. This is 10,560 feet, or that's 2 miles, because 1 mile is 5,280 feet. And this angle is 45 degrees. So this total angle between the 2 mile length and 360 times time speed is 360 miles per hour times time, where time must be in hour to be consistent. Then this is the triangle to be considered. We apply cosine law to derive S in terms of t. So S is square root of quantity 360t square plus 2 square minus 2 times 360t times 2 cosine of the angle between 360t and 2 miles, 135 degrees, 90 plus 45. So your calculator is now capable of evaluating this. There's only one variable in the right side. So using the calculator technique with t 1 over 60, you'll get 3.5 353.6 miles per hour. So again, you type this in your calculator naturally, then evaluate the derivative with t 1 over 60 hour, or 1 minute, that's 1 over 60 hour. You'll get that. So likewise, by the traditional solution, so we have 60 S is square root of 360 square t square plus 4. Then combining this, that's positive. So 360 square t square plus 4 plus positive 1018.23 t. So again, we have square root of u. So the derivative of this ds dt is derivative of inside, then divide by 2 square root of, we just copy. So that is 360 squared times 2t, then plus 1018.23 divided by 2 square root of 360 squared t squared plus 4 plus 1018.23, or plus 1018.23 t plus 4. It's the same. So substituting t equals 1 over 60, then we can show that ds dt is also 343.6 miles per hour. So that's it for this video.